Okay, let's go for the next experiment. In this case, we have simple harmonic motion. For simple harmonic motion in mechanics, we have two special cases. One is using springs and the other one using pendulums. Both of these object devices produces a simple harmonic motion, correct? Now, let's see what happens when we have the spring first. According to Hooke's law, right, the force done by the spring is equals to kx. In this case, let's try to find k using two techniques, two ways. One, adding masses to the spring, and the other one, make oscillate the spring with certain masses. Okay, increasing the masses. Great. And now let's compare this to the spring constant. There, and the theory must be the same. Let's see how close we can get these two values. Okay, first, let's go to the case where it's static, right? We place a mass and then as the length increases, another mass increases, right, and so on. We call this a static K, spring constant. The other one, the same thing, right? We have a mass, let me oscillate, right? Another mass oscillate, slower, another mass, right? Oscillate, right? And in these two cases, K, the spring constant, is the same. Okay, let's compare these two cases. Spring constant. First, we have the spring, we add the mass, right, and we have that the spring stretches, right, this distance x. According to Hooke's law, right, if we solve for k, the spring constant, is going to be force, which is the weight of this mass divided by x, correct? Let's repeat this for different masses. Let's increase the mass, right? When we increase the mass, x increases. Let's make a table for this. We have, for example, 50 grams, 100 grams, 150, 200, and 250, 100 grams, correct? And let's find x for each case, right? And then let's find force. Remember, force is just the weight equals to force mg, correct? And from here, we solve for, we find k, right, for each case, k. Now we can find the average. The average of k, let's label it as Ks, right? For S stands for static case. Perfect. Also, we can use Excel, right? Using the slope, we can find also K. Perfect. Now, let's compare this K to the case again when the mass oscillates, right? We know that the period for oscillation of the spring is equal to 2 pi square root mass divided by the spring constant. Now, because we're looking for k, let's cancel the square root, taking the square of both sides, right? And then we have the period square equals to 4 pi square mass divided by the spring constant. But because this is the spring constant for the case when we have oscillations, let's label it KD. This stands for dynamics. Okay. Now, the same thing before, let's use different masses. Let's find the time of oscillation, right? For, let's say, the time for 10 oscillations. And then let's divide the total time by 10 to find the time of the period, right, for one oscillation. Then let's take the square, because when we are looking for, right, the graph t squared versus mass. Let's increase the mass, the same thing, repeat the procedure. Let's find the time for 10 oscillations, right? Divided by 10 to find the time only for one oscillation, which is going to be the period, and then take the square, and so on. We can take, right, 3 or 4 masses for this experiment. Again, let's plot these two quantities, and let's label the slope to be a, right? And then, because this is similar to a linear equation, right? We have y equals to mx. Y now is t squared, correct? And m is gonna be, right, the slope. This is gonna be the slope in this case, correct? So a is gonna be to 4 pi squared over kd according to this notation. Now let's solve for kd. It's gonna be 4 pi squared divided by a, the slope. Let's find the answer, and at the end, let's calculate the percent error. Correct? It's gonna be ks minus kd, absolute value to avoid negative signs, divided by the average of these two values times 100%. Correct? Now let's move to the next case, case 2. using pendulum. Okay, in this case, let's try to find the, in this case we're looking for G theoretical, which is, as you know, 9.80 meters per second squared. Let's see how we can calculate it using this way, right? The pendulum. We know that the period for a pendulum is equal to 2 pi square root L over G. L is the length of the pendulum. Great. Now, the same thing as before, let's take the square. We have T squared, which is the period, correct? Equals 4 pi squared L divided by G. Okay. Now, in this situation, we are plotting T squared versus L. So it means that we need to increase L and then find the period for each length. Okay, for this case, we have 20 centimeters, right? 30, 40, 50 centimeters for L. Now, because we're looking for the period, let's repeat the same procedure as before. Let's make the pendulum oscillate 10 times. And then let's divide that time, the total time, for 10 oscillations, right? Divided by 10 to have the time for one period, the time of the period, right? And then take the square, right? Repeat the same for the other lengths, right? And let's plot this data. Let's plot T squared, right, versus L, the length, correct? And let's find the slope. In this case, the slope is gonna be this quantity, right? This quantity is B in this notation. So B is the slope, right, equals to 4 pi squared over G. Let's search for G. So G is equals to what then? 4 pi squared over B. This is from the experiment. Okay, let's find the value. Meters per second squared, correct? And let's compare that to the theoretical value. What is the theoretical value? The theoretical value for G theoretical is equals to 9.80 meters per second squared. That's the theoretical value. Let's compare that value to the experimental one, which is coming right, or is related to the slope, correct? And find the percent error. Okay, now let's do this experiment. I'm gonna show you all the data that you need to collect, right? And using that data, you can find all of these quantities. Okay, let's do it. Okay, let's go for the experiment. Case 1 using springs. Let's find KS. Okay, this is our reference level right here. Imagine this is for mass equals 0. We have no mass added. We use this mass only to take as a reference. Okay, imagine that we start at 0. Now let's add masses. Then the next mass is gonna be 50 grams according to the table, correct? So we have 50 grams. Now let's look for X1. Okay, please try to approach, right, what should be X1 when mass is 50 grams. Now let's add 50 more, so the total is gonna be 100 grams. Okay, for 100 grams, what is the total length? Okay, the total length, right, when we add another 50 grams, towards 100 grams, correct? Our 0 is right there, always starting from 0. Okay, so for the example for 100 grams, we have about what? About 5 centimeters, correct? Now, another 50 grams. Another 50 grams is coming. Oops. Now let's find the new length, right? Let's use this as a reference, correct? And let's find the new length for 150 grams. Let's add another 50 grams, and now we have the total. The total is 200 grams, correct? 200 grams. Okay, now we have 200 grams. Perfect. Now find the new length, okay, for 200 grams. And finally, 250 grams. So we have 250 grams. And what should be the total length? Remember, always starting from 0. For example, for this one, right, you start from 0. This is about what? About kind of what? 12.5 or 13. You you just figure it out. Okay, let me lower down the camera to make sure that we are at the same level. Correct, the same level. Can you see it? Now you can approx right here, this level, approx the distance, okay, is in centimeters. Later you have to convert it to meters. Okay, great. This is case 1 part 1. Let's go to case 1 part 2, when the masses oscillate. Okay, let's do it. Okay, let's go for case 2, case 1 part 2, when we have the masses oscillating. In this case, we have 100 grams. Now they are oscillating, right? Let me make it oscillate. For you, you are supposed to count 10 oscillations. To do that, please, let's take this point as a reference. You're supposed to use your stopwatch from your cell phone, right? And count 10 oscillations. For example, look, it's gonna be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 10 oscillations. You have to write the time. Imagine that the time is 7 seconds. Now let's divide that by 10 to get the time for 1 oscillation, correct? And later take that time, the time for the period 1 oscillation square, correct? Can you see it? Perfect. So you can count again. You can start at any time, right? Start the counting. You place your clock on your cell phone, right? And find the time for 10 oscillations. Remember, you are taking 1 point as a reference. Could be the bottom one or the top one. Don't take the middle one. Could be at the bottom. It's like 0, 1, 2, 3, and so on to 10. Always start from 0, right? 0, 1, 2, 3, 10. Correct? And then the total time is divided by 10 to find the time only for 1 oscillation. Correct? Okay, this is for 100 grams. Let's go for 150 grams. Okay, now we have 150 grams coming. Perfect. Now let's make it oscillate. And the same thing, please count 10 oscillations and track the time for those 10 oscillations. Okay, remember, always start from 0. Okay, let me do it one more time. Okay, you can take it at any time, right? Must be 10 oscillations. Okay, now let's go for 200 grams. Yes, 200 grams. The same thing. Okay, it's gonna be very nice. Okay, you count again 10 oscillations. You start at any time as long as you have, right, 10 oscillations, the total time. Then divided by 10 to have the time only for 1 oscillation. Perfect. Now let's go to the last mass, which is gonna be 250 grams. Okay, 250 grams. The same thing. Okay, let's count 10 oscillations. Again, could we look? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? And then that time is divided by 10 to have the time only for 1 oscillation. Then take the square. Just follow, right? Follow the table that was provided before on the whiteboard. Correct? Now let's go to case 2. Using the pendulum. Yes. Okay, let's go now for pendulum. In this case, we have L, the length, is gonna be about 20 centimeters, right? L goes from this point to the center of this sphere. It's gonna be 20 centimeters. Okay, and let's repeat the procedure. Let's oscillate, right, the pendulum. And the same thing, right? Let's count. For example, look, we start at this position. We have our stopwatch, and we said 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 oscillations, right? So you have the time for 10 oscillations. Divide that time by 10 to have the time only for one oscillation, which is gonna be the period, and then follow the table that is on the whiteboard. Correct? Perfect. This is again the time for the length of 20 centimeters. Correct? Now let's go to 30 centimeters. Let's do it. Okay, let's go to 30 centimeters. In this case, let's remove this masking tape a little bit, right? Perfect. Let's increase length, correct? Let's increase the length. The length is coming. Now, let's make sure that we have 30 centimeters. Okay, a little bit up, 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 correct? So more or less, that's gonna be, correct, 30 centimeters. Perfect. So we have more or less 30 centimeters right there, correct? Let's fix that length and let's make it oscillate again. Got it? Okay, great. Let's do it. Okay, it's right here. Perfect. Okay, let's do it. And the same thing, remember, count 10 oscillations. Start, let's say right here, look, right here. Take this point as a reference and start counting, starting from 0 all the time. Okay. This is for 30 centimeters. Now let's go to 40 centimeters. Okay, let me stop right here a little bit. 40 centimeters. Okay, now let's go for 40 centimeters. Actually, the oscillation must be small angles, right, to have a more precise measurement, correct? So this angle is enough. Please start counting at any time you want to, correct? Starting from 0 all the time. The length for this one is 40 centimeters. Okay, now let's go for 50 centimeters. Yes. Now let's go for the case when we have 50 centimeters L, right? Let's do it. Let's repeat again the procedure. Okay, please count the time for 10 oscillations, right? Starting again from 0 to 10, and divide that time by 10 to have the time of the period. Great. Now let's use again the square of the period and plot this with the length, right, as was explained before, right, using the whiteboard. We can use Excel again to find the slope, and just proceed right according to the theory was explained before. From here we get the data, right, for the time, right, for pendulum, and compare that again to G, the theoretical value, which is 9.80 meters per second square, and let's see how close we are using this experiment. Great. See you in the next experiment. Bye.